In this video, we're going to start to get into the actual structure of different types of compounds with a quick sort of comparison of how ionic versus covalent compounds tend to exist. We're going to be talking a lot more about covalent structure in particular in the next several videos, but I want to give a brief introduction to kind of how that's different from ionic first. So ionic compounds tend to exist. Well, first, we know that ionic compounds are comprised of positively charged cations and negatively charged anions that are attracted to one another via ionic bonding. So when you have a solid ionic compound, let's think about sodium chloride, typical table salt. We know that opposites attract and like charges repel one another. So that means that the cations and anions are going to be attracted to one another, and that doesn't stop at just one cation and one anion being attracted. That actually goes in all directions in 3 dimensions, and that idea of opposite charges attracting one another is what gives rise to the way that ionic compounds exist, which is as an extended lattice structure of like rows and columns. With alternating ion charges. So if we think about what this would look like at the molecular level, so let's, for example, consider what the structure of sodium chloride would actually be. Sodium and chloride are each just a single atom, ion, a monatomic ion. So let's say that red is going to represent our sodium ions, and green, did not mean to make this Christmas, but oh well, green is going to represent our chloride ions. So we think about NaCl as being one sodium with one chloride, but it's not really how it exists. It's never just one atom of each. It is a 1-to-1 ratio is what our formula is really representing. So what we really get is this alternating pattern of this negative ion wants to be next to a positive ion because that's going to be an attractive force. But it doesn't have to just be next to one. It can be attracted to multiple ions on multiple sides. So we end up getting this alternating pattern of positives and negatives that extends in 3 dimensions. I'm just going to draw it in 2 because otherwise it gets real confusing real fast. So you can imagine, I'm going to take the lazy way. Beautiful. You can imagine sort of stacking these types of layers on top of one another so that we end up with this negative ion is completely surrounded by positives on all sides. So there would also be like a positive on top and a positive below it if we're imagining sort of stacking these layers. So this maximizes the attractive interactions between our ions because we're creating all of these different interactions between oppositely charged ions. So in a crystal of table salt, this is the sort of structure that you have of alternating positives and negatives that extend out in all directions. So this is, in general, how ionic compounds exist. There are some different 3-dimensional arrangements that are a little bit less straightforward alternation if you don't have a 1-to-1 ratio, but they generally follow this same principle of alternating charges as much as possible, maximizing those attractive interactions. So Again, sort of the important thing to remember here is that the formula for an ionic compound is actually what we call an empirical formula. Which means it shows the simplest whole number ratio of atoms of each element. But not the exact number that are actually connected. So in this diagram here, every place where you have a positive next to a negative, a sodium next to a chloride, is an ionic bond. So there's an ionic bond here, there's an ionic bond here, 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 here. You get the picture that every place where there's an attraction between ions is an ionic bond. So when we write the formula NaCl or any ionic compound, we're not specifically saying one sodium is bonded to one chlorine. We are saying that in this sample, there is a 1-to-1 ratio of sodium to chloride ions. There are equal numbers of sodium to chloride ions, and that is what the formulas for ionic compounds are intended to express, and what this idea of an empirical formula is intended to express. This is very much in contrast to covalent compounds, which do not exist like this most of the time. So for covalent compounds, most of the time there are some counterexamples of this. Most exist as individual molecules. Which are groups of specific numbers of atoms. And molecules are not connected to one another. So, for instance, water is probably a familiar compound to you, is H2O. We're going to get into structure drawing in the next couple of videos, but you've probably seen the structure of water drawn before, as the oxygen is in the middle and the hydrogens are on either side. This is a water molecule. It has exactly one oxygen atom connected to exactly two hydrogen atoms. It is not a ratio, it is an exact number. So a water molecule always has exactly one oxygen connected to two hydrogens, not just a 2-to-1 ratio. So for covalent compounds, the formulas that we use are what are known as molecular formulas, which give the exact number of atoms of each type. Not just the ratio. So water is always exactly one oxygen connected to 2 hydrogen, not simply 1-to-2 ratio. So our formulas for ionic versus covalent compounds describe slightly different things, and that's because of the way these typically exist. So in the next several videos, we're going to be learning how we can figure out the structure of simple covalent compounds, since they tend to follow a relatively straightforward set of rules.